So where are we at? Where are we going with the story? All right, so we finally arrived at the definition of what a determinant is. By a determinant, we mean a very specific type of function. It takes matrices and spits out real numbers, and it does a couple of things. So first of all, it's row linear, meaning that if I have a trio of matrices where one of the rows is a linear combo and the other rows are held fixed, then the mapping acts linearly. It is alternating, meaning that if I have distinct rows equal to each other, then the value of d of a is 0. And the thing that makes it a determinant is if it sends the identity to 1. All right, and as we noted, our favorite magic number for 2x2 matrices, AD minus BC, is indeed a determinant. We've already discussed that this must be real linear. We have verified that it is alternating, and it is clearly a determinant since it very obviously sends the identity to 1. All right, so our goal, again, is to basically verify that determinants, when present, must be unique. So that would be the first thing we hit, is that determinants are unique entities. Then that only leaves us to prove that a determinant must exist for every n by n matrix, and thus we have the existence of the function we call the determinant. And as we've been going here, we've been proving a whole bunch of properties. So specifically, we verified that invertibility is equivalent to your determinant being non-zero. And as pointed out by Steve there, this was a very beautiful proof. Very comfy proof. All right. Okay, then the next fact that we proved was that determinants are multiplicative, meaning that the determinant of a product is the product of determinants. This is an incredibly essential fact, and a fact that is incredibly difficult to prove using the recursive definition for the determinant, but going the alternating row linear route, it's pretty easy. It kind of just pops out for free. It's good proof. All right, and as I noted, this is incredibly essential, and we'll see repeated use of this once we get into eigenvalues, which will hopefully be later this week. All right, and equipped with that, we get this nice formula for the inverse. The determinant of an inverse is 1 over the determinant. So nothing magical there, it just behaves nicely. All right. And then we get into the uniqueness. So we first verified that for 2x2 matrices, indeed, the only determinant that could possibly ever exist is our favorite magic number, AD minus BC. And we noted that the proof of this, which we did in excruciating detail, really reveals kind of what happens for 3x3, 4x4, so on and so forth. And kind of the key step is to recognize that the rows of any matrix are a linear combination of the rows of the identity. So then by setting up appropriate matrices with the rows of the identity in the appropriate spot, you can now start applying the row linearity to pull this apart into a summation. And each of these submatrices that we're creating, by the alternating and the property of determinants sending the identity to 1, we can verify that these have to line up with the appropriate constants, and we worked out the details of that. Basically because they can also be split up into matrices whose rows of the identities appropriately chosen, so that when we do the linear combo, these things are spitting out 0 or plus or minus 1. Plus 1 in this case, minus 1 in this case. Okay, so that's where we ended off. So exactly what we just described there is going to work for any size matrix. It just becomes an index fest that you need to be careful about. Okay. So here's the basic gist. So let's say you do have a determinant defined on the n by n matrices. Take any matrix. Every row is a linear combination of the rows of the identity. This is pretty easily verified. Just plug in an index here, and you'll note that this dies for anything other than the number you plugged in here, which will isolate the index that we want. Note, this kind of looks like a matrix product that's going down. All right. Neat. All right, so equipped with this knowledge, then the row linearity guarantees that we can rewrite d of a as a linear combination of the entries of the first row of A times the determinant evaluated at some matrices B, where the matrices B, the first row, are appropriate rows of the identity. And the other rows are held fixed. And then we repeat. right? So we repeat this process. So for each b sub k, we find a collection of c sub hk's that run from 1 to n, where the first row of the ck's is the first row of the bk, and then their second row is the appropriate row of the identity matrix, and then the other rows are held fixed. So specifically, then, this can be rewritten as a summation as follows. We're summing over indices j and k. They run from 1 to n, where the first index goes there, the second index goes here, and basically the matrices that end up in here, their first row must be the jth row of the identity, and their second row must be the kth row of the identity, because that's how we're picking all of these matrices. The other rows of C are held fixed. In other words, they line up with the appropriate rows of A. And then you repeat this until you exhaust all of the rows, and that means you'll end up with this sort of god-awful expression where you've got n indices running around. They all sum from 1 to n, and the only things we need to be keeping track of is that k1 here is the index that goes there, k2 is the index that would go for a2, all the way up to here, and the matrices that we end up here, are going to be just matrices whose rows are the identity matrices, the rows of the identity matrix, where they've just been scrambled, essentially. And the notation here is to represent that k sub 1, that is precisely what the first row of this is in terms of the identity matrix. Right, so note that the B's here, the first row are identity matrices. B1 has the first row of the identity matrix in its first row. B2 has the second row of the identity matrix in its first row, so on and so forth. Then the C's we create have those first row patterns, but for each one, you go for a different permutation. So, for example, when J is equal to 1, right, then, so that's in the case here when K is 1, and then you run for all the possibilities here. So then the second row is the first row of the identity. Then we go to the next one where the second row is the second row of the identity, so on and so forth. So you just do this, and ultimately you get down at the end where you've pulled out all the coefficients and you're multiplying by D, evaluated at these matrices, where it's basically every possible mutation of the identity matrix with double counting. So it's possible in here that we're picking up matrices where we've got the identity matrix and the first row and the second row are the same thing. Right, so for example, if we're looking at this, B1 has the first row of the identity matrix in its first row, and the C sub H1 here will also have the first row of the identity matrix in its second row. So if you're being really careful and you're really dissecting how this is all pulling out, basically what we'll get here is every possible combination of the rows of the identity with repetition. So you're allowed to just repeat rows. Okay. But, so note at this point, all that's used here to do this is the row linearity. Row linearity guarantees this, but we don't like that idea of repeating rows. That's why alternating is a nice assumption to have here, because now if I look at this, basically a whole bunch of these are going to equal 0. So specifically, since D is alternating, if any of these indices are equal to each other for any two distinct ones, so in other words, if I have a matrix that is a bunch of rows of the identity and I repeated, let's say, row 4 in two different spots, then the zero's out because it's alternating. And that was the nice property of that. If you have distinct rows that are equal, then this just zeroes out. So in other words, our expression there, the only terms that will actually appear is when this is a distinct set, when this is just a collection of n distinct real numbers. But note, these are all coming out of the set 1, 2, 3, all the way to n. So in other words, this has to be a permutation. So it's just some scrambling of the numbers 1, 2, 3, all the way up to n. So in other words, I can find a 1-to-1 and onto function so that sigma of j is k sub j. Right, so the alternating basically guarantees that we can delete any of the matrices where we saw repeated rows. And we saw that in the 2x2 case, where we repeated the first row of the identity and repeated the second row of the identity. We were able to just go, well, those are zeros. All right, so a permutation of the set of natural numbers from 1 to n is just a bijection. So it just scrambles it, and that's it. No repetition, and just, right? So a permutation of, say, 1, 2, 3 is 3, 1, 2. That's all these are. Now, in light of that, that means the summation actually turns into this. So here we have our a sub 1 k1, a sub 2 k2, all the way down to a sub n kn. But now the only kn's that we care, the only k's that we care about are the ones where this is a distinct set. So in other words, the ones where these have a permutation associated with them. So the summation now, instead of being over all possible combinations of natural numbers from 1 to n, really it's just all over all of the possible permutations. Right, there we go. So the summation cleans up quite a bit because there are a bunch of these we just don't even need to consider because we just have a whole bunch of zeros. All right, so the only identity matrices that we are going to look at inside of the determinant are the identity matrices that have a distinct scrambling of the rows. Okay, so some deep lore here before we go forward. The collection of all permutations of 1 to n is called the symmetric group. It has n factorial things in it, which is pretty easy to verify. Think about the first term has n choices. The second term has n minus 1 choices because you already exhausted one. And then so on and so forth. So there's n factorial possible bijections of the set 1n to itself. The fact that it's called the symmetric group, once you take Math 301, this will become a little bit more obvious. And there's also something called the alternating group. So, yeah. There's some deep math here that we're kind of sidestepping. But anyway, all right, you'll see in the Math 301. Don't worry. All right. So now what do we want to do? Well, it turns out that, well, hey, I just have a scrambling of the identity matrix. A determinant sends the identity matrix to 1, and a scrambling of the identity matrix here is just a bunch of type 1 row operations. So, since any permutation just gives me a rearrangement of the identity matrix, that just means there's a bunch of type 1 elementary matrices that it's equal to. So you've taken the rows and you've just scrambled them, so just apply a bunch of type 1s until you get that matrix. So any scrambling is basically just a scrambling pairwise. So was it like bubble sort or something? Is that the one where you just like go down and look at the adjacent ones and keep swapping them until they get in order? Anybody know any of this dumb algorithm stuff? Any filthy computer scientists here? I barely remember this stuff. I took comp sci. Shush! Yeah, get out of here. I took the equivalent of COMS 227 and COMS 228 at the school I went to. I got through COMS 227 pretty easily. COMS 228, though, I was like, "This is what the hell is this?" I failed it, and then I had to take it again. So, oh well, no, actually, let me take that back. I didn't fail. I dropped when I was like, "Oh boy, I'm gonna fail. Let me not even deal with this."
Every year with the algorithms class, Comp Sci 311, a couple people come over from the math department and just wreck the curve for everyone.
Nice.
They usually just smoke everyone on all the exams. It's actually a little upsetting.
I'm sorry about that. Anyway. All right, but yeah, so all of these matrices here are just a scrambling of the identity, which means I can just write it as a product of type 1 elementary matrices. And since we are an alternating row linear mapping, that means we send the identity to 1. And all of these, as we noted, these are type 1. So since we're alternating, all these do are introduce a -1. So alternating the sign, plus or minus. So whatever this is equal to, it's just some power of m. It's just some power of -1. And in particular, because this is a function, and here's the fun part. Since this is a function, it only ever spits out one value. Which means that the m that we found here can only ever be odd or even. It can't never, there's no possibility of finding an M and an N that both work and they have different parity. That would violate that this is a function. So this actually also then verifies sort of sneakily that any rearrangement of the identity matrix that you can only get there doing an even number or an odd number of swaps. There's no way if you do a scrambling and you get and use an even number of steps to scramble it. You can only ever get there by an even number of steps. There's no way to get there by an odd number, because if you did that, well, this here is -1 to the m. If you had an even number of steps and an odd number of steps, you would get that -1 is equal to 1, which is a bull. So we sneakily proved something pretty neat there. But anyway, so this value actually has a name. It's called the sign of the permutation. This is also called the signature of the permutation. Either way, you call it SGN. And so note that it's only ever 1 or -1. It's 1 if an even number of type 1 row operations turns this back into the identity, and -1 if it's an odd number. And note that if it was an even number that gets you back to the identity, there can only ever be an even number that works. You couldn't do an odd number, because then you would get -1 is equal to 1. Not that we need this fact, but just worth pointing out that we technically kind of proved it. But anyway, so equipped with all of this knowledge now, we arrive at what's called the permutation formula for a determinant. So specifically, we now know that for any determinant, its output is always just go down the rows, select elements, add them all up, and then throw in appropriate pluses and minuses. So, hey, note, this is a linear combination of the row linear mappings that we first discussed. So, as we've now verified, this is the only formula that you could ever have for a determinant. It's a linear combination of the basic row linear mappings, where the column entries you pick, you need to pick them without repetition. So you go down your rows, you pick your column entries, and you got to make sure you pick everyone exactly once. And then you throw in a plus or a minus, depending on the key property of the permutation. How many type 1 row operations do we need to apply to the identity matrix to get you to this matrix? All right, so in other words, if determinants actually exist, they have to be unique, because they all have to have this formula. There is a formula. This is what they must equal. So this is known as the permutation formula of a determinant. It's not the recursive formula, which we will be getting to. But the permutation formula is really nice, even though at first glance it looks a little daunting. So it's a summation over all possible permutations of the integers from 1 to n. And you do that. So if you add a fun little exercise, do it for 2x2s, and you see everything lines up correctly. So before we go on to verify the recursive definition, now that we've got this knowledge, you can actually use the permutation formula to quickly prove a couple of important facts about determinants. So let's do that before we discuss how do you create the 3x3 determinant, how you create the 4x4. And note that if we create a 3x3 determinant, it is unique. So we've proven uniqueness first, and we will soon show existence. But before we do that, let's use this permutation formula to verify a couple of facts about determinants. So the first one, which is a fun fact about determinants, is that the determinant of a transpose is the determinant of the original. So transposing does not affect the value of a determinant. Now, again, this is a fact that you can prove using the recursive formula, but that proof especially, out of all the proofs that you can get with the recursive formula for the determinant, that proof especially is completely and utterly uninstructive and is just a recursive induction nightmare to get it to work. It's an awful proof, and it's just basically moving around a bunch of symbols and just like, all right, I did it. This proof, using the permutation formula, though, I think it's the only proof of this fact that I've ever seen where I'm like, oh, I get why that's true. Right, because the recursive proof is just a mess of things. But this proof right here that we're about to do gives a really clear justification for why this ends up happening, because the permutation formula for the derivative, if you look at A transpose, well, the permutation formula gives you this. What does transposing do? Well, it swaps the rows and the columns. All right. Well, what are these sigmas again? These are permutations, so they have formal inverses. That means that I can scramble this and rearrange it so it looks like that. Right? Because one of these outputs, right, one of these sigmas is 1. So you just take that and put it first. Then there is another sigma that spits out 2. So you make that the second term. And note that if you've got sigma, let's say sigma j is equal to 1, well, that means j is equal to sigma inverse of 1. So all of these here, we can just rearrange them so they look like that. So, hey, that almost looks like the permutation formula. We've just now, instead of having sigmas, we have sigma inverses. So that's going to be the key ingredient of the proof. We're basically going to replace all the sigmas with sigma inverses, and basically all that meant was that we just, instead of summing up over all of the permutations, we summed up over all of the inverses of permutations, but the collection of all inverses of permutations is just a collection of all permutations. So we're done. So for me, this is always the proof that I was like, oh, this like clearly explains why it works. You know, I mean, you can of course verify it with the recursive formula, but it's like, woof. It's just like, yeah, sure, I guess. But again, this is another very important fact about determinants, and our approach has furnished a comfy proof of it. All right, so let's finish it off. So we replace all of these with sigma inverses. So now we need to turn this into a sigma inverse. And why would that be true? Well, let's remember what this is. This gives me -1 to the m, where that's a number of type 1 row elementary matrices, so that the product of these has those as its rows. All right, well, the inverse of this then must have those as its rows, since if I take the product of all of them, I got to get to the identity matrix. So here we did a bunch of type 1 row operations, and remember the inverse of a type 1 row operation is another type 1 row operation. So this takes the identity and scrambles it into the matrix whose rows are these, and applying these type 1 row operations gets us back to the identity. That means these must be those rows. These are the ones that undo sigma. That's its inverse. So in other words, the number of row operations that transform these into the identity, right, must be m as well. And so there we go. The sign of sigma and the sign of sigma inverse must equal each other. Right, since here the number of maneuvers to create the matrix with those as its rows is precisely m. So it must be the same number. Oh, hooray! We did it. Okay, so we verified that you can view these involving sigma inverse, and now we've got that in terms of sigma inverse. So if we return to that, we now have that the determinant of the transpose is this now. We can rearrange these so they all involve sigma inverse. The sign of sigma is the same as sign of sigma inverse. So the summation now is, instead of doing all of the permutations, do all of the inverses of the permutations, but every permutation's inverse is another permutation, and that's itself just a rearrangement of the collection of permutations. So that means the summation is just over the collection of all permutations, so just rearrange it so you're not summing the inverses, but rather summing the originals. And then, hey, that's just the determinant. So we're done. Yay. So, I do want to note, it's mildly hand wavy. There's some facts about permutations that I'm using here that we haven't quite proven, but you'll see more solid proofs of these. Remember, a permutation is just a rearrangement of the numbers from 1 to n. And in fact, in general, you can talk about permutations of any collection, any finite set. You can just permutate however you want. But note that the way the symbols are labeled. Yeah, hope that wasn't too awful. And like I said, this is the only proof I've seen for this fact that the determinant of a transpose is the determinant of the original. That really kind of reveals why it's happening. Because when you look at the transpose, it swaps the location of the sigmas, and then so you just apply sigma inverse, and then but it all comes out nicely. Ooh. You're right. So that's the first easy proof using the permutation formula I wanted to include. And now the next one is the following. So let's say you've got a matrix with the following property. A sub jk is 0 whenever j is less than k. So in other words, whenever the row you're in is less than the column you're in, you equal 0. So if you want to think about this for a moment, let's say we're in row 2, column 1, we must equal 0. The other way around, sorry. Whenever we're in row 1 and then we're in column 2, we must equal 0. So matrices that satisfy this are called upper triangular. Right now, this would be the other way. So if we were in row 2, column 1, then this would be satisfied to equal 0. So these are the lower triangular matrices. So a upper triangular matrix is one where everything above the diagonal is equal to 0. That's what this is equal to. This is a lower triangular matrix, everything below the diagonal is 0. And note that those have super easy determinants to compute. You just product up the diagonal. So the tricky way of computing determinants is to start off with a matrix, do a bunch of row operations, make it upper triangular, and then keep track of your row operations to see which specific row maneuvers you do. So that keeps track of the non-zero scalar for the row equivalents, and then you just multiply up the diagonal at the end. So every matrix, every square matrix is a row equivalent to an upper triangular. So this is a slick way of getting the determinant numerically without having to compute a whole bunch of stuff, but it's still a bit of a pain. Anyway, it's a lot less than directly computing it. Anyway, all right, so let's quickly prove this. It's pretty easy. So take any permutation so that this product is indeed 0. All right, well, spoilers, what does that mean? Well, that means all of the entries here have to satisfy this. Right? If k was strictly less than sigma k, then one of these would have to be 0, which gives you the product. So the only way you have a product that is non-zero is if sigma k is less than k, but this is a rearrangement of the numbers from 1 to n. So sigma of 1 is less than 1 means that sigma 1 must be 1. Sigma 2 is less than 2. Well, all right, sigma 1 is 1, so sigma 2 can't be 1, but it's got to be less than 2, so it's got to be 2, so on and so forth. So that forces all of the sigma k's to be that. So the only product of these elements, so you go down your row and you pick things and you multiply it up, the only product that is possibly non-zero is where the permutation is the identity. So for any other permutation, the product must equal 0. That can be proven maybe a little bit more directly by going any permutation that's not the identity has to have a j less than sigma j or something like that. But anyway, equipped with that, we then know here that the summation is basically just a summation of a bunch of zeros, except for the identity permutation, which is potentially non-zero. It could equal 0, but we know for a fact that the only terms here that are definitely non-zero, that are definitely possibly non-zero, is this one. Because if it is non-zero, it must be the identity. So if you have a non-identity permutation, we know the product must equal 0 by contraposition. So basically, all of these terms drop out except for the identity permutations. Yeah, you just get the product of the diagonal. So another very important fact about determinants that is frequently used that we have now cleanly proven. I do want to note, actually, the recursive proof on this one is not bad. This is one of the few ones where it's actually like, it's basically the exact same proof as this. In a sense that this proof here is actually a little bit more overkill than the recursive proof, but we're in the spot, so we might as well do it. So, like I said, this is another important fact of determinants where if you've got a triangular matrix, again, that's formally described by enforcing these things here, then its determinant is just the product of its diagonal. So a trick to efficiently compute the determinant is to hit it with some row operations, keep track of the row operations you do, get a diagonal matrix, multiply it by the diagonal, and then multiply whatever non-zero factors showed up by doing all the row operations. So that gives you a that's an order n squared algorithm. So not too bad. Still not a great one. I think that's the best you can do. I think it's been proven it's the optimal algorithm for determinants. I vaguely remember from my graduate class that let's see what Stack Overflow says. Ooh, the LU decomposition. Maybe that might be the fastest. I wonder what's the big O? That's what I'm interested in. It's a quick random. Let's see. Okay, the LU that's order n cubed. That's still not good. It's the best one that's not. Order n squared. Oh, so that actually is an order n squared, the one that I said. Apparently that's still. Okay, so the best algorithm that's known is n to the 2.376. So sure. So yeah, actually computing the determinant. This is one way of getting there. It's not too bad. How's that? I don't see why that isn't. Actually, you got to do a product, so I guess that'll probably make it n cubed. Anyway, algorithms are dumb. Okay, all right, and B, the proof there is basically exactly the same, only this one gets flipped. All right, so with all of this said now, let us begin the process of finally getting to the recursive formula. So our final goal now is to basically establish the recursive formula. And the way to do that is to introduce some new things. So the first thing we need to introduce is this Kronecker delta. So this is a function defined on the integers direct product with themselves, and it spits out an integer. Specifically, if the indices here are equal, it spits out 1, and if the indices are different, it spits out 0. So, for example, the identity matrix is just defined by picking the entries of the Kronecker delta. So the Kronecker delta shows up a lot in mathematics, and it's got a lot of kind of neat basic properties that we will exploit here. But why do I want to include this? Well, I want to include this because, as we noted, the recursive formula for the determinant requires us to take a row and a column and delete them from the matrix. So we want to be able to describe being able to do that using some sort of method. Now, if we think about it, that's an operation acting on the rows and the columns. Now, the row operations that we discussed, we were able to represent them as matrix multiplications. It turns out that deleting a row and deleting a column can also be represented as matrix multiplications, and the way to do it is to first do it to the identity matrix and then do the multiplication. Okay. So the identity matrix with its pth row removed is the following matrix. Its jkth entry is the Kronecker delta. If the row we're in is not the pth row, any row before the pth row. And then once we've hit the pth row and beyond, we then shift by 1 in the rows. So this takes the identity matrix and just removes one of the rows first. So if you were to look at the 3x3 identity matrix, then R2 deletes the second row. Right, so you'll end up with a 2x3 matrix. specifically 100001. And here it is more formally stated. Okay, and then similarly, we can define the identity matrix with its PIF column removed by doing the exact same thing, where if the column we're in is not the PIF one, then we don't change anything. But if the column we're in is P and beyond, we then shift. It should be a K there, not a J. I totally did not copy and paste and change any of that. That's not what I did at all. Nobody ever does that. Yeah, come on. This file is really big, so it takes a little bit longer. Yeah. All right. So these are the identity matrices where we've removed a specific column and removed a specific matrix. And multiplying any matrix by these will do exactly these processes. So, for example, if we were to take an n by n matrix, and here we need n to be greater than 2, otherwise all these things don't make any sense. So if we were to look at A times RP, note that this matrix that we would get here, first of all, if we're thinking about its dimension, this is an n by n matrix. This is an n minus 1 by n matrix. So the product here has n minus 1 rows. And likewise, here, this product would have n minus 1 columns. So here we see that if I look at the jth row of RP times A, well, if I'm not up to P yet, then the matrix hasn't changed. But once I get where P should have been, then the matrix jumps forward and the P row is missing. And likewise, for C and D, we get the same thing. So indeed, here we go. This is the way to actually delete rows and columns out of your matrix. You can do it via matrix multiplication. That's a very nice move. Being able to describe these sorts of row and column modifications using matrix multiplication is an incredibly powerful tool, and it lets us get away with a lot. In the same way that row operations are just multiplying by certain matrices, deleting rows and columns are just multiplying by certain matrices. Note that in order to delete a row, we multiply on the left. In order to delete a column, we multiply on the right. All right, so I'll work through A and B in a bit of detail. C and D are just basically the same proof. It's not anything too particularly interesting, but it'll be there if you want to see it. But anyway, so let's do the multiplication. So if J here is less than P, well, then if we look at this is a matrix multiplication. And then as we noted, this will spit out the Kronecker delta, as usual. And what does this do as h runs from 1 to n? Well, when it hits j, it's equal to 1, and for any other, it doesn't equal it, so it just deletes it. And so there we go. Here we see that these lined up accordingly, and we're nice and happy. Okay, so now for B, let's say now we're looking at a row that has equaled P, is possibly bigger. Well, then if we look at the product again, note that since we are beyond the P row, we don't get the normal Kronecker delta, we get the Kronecker delta shifted by 1, which means as h runs from 1 to n, what it's actually going to pick up is the j plus 1 entry. So it shifted the row accordingly. And there we go. Beautiful. All right, so indeed, multiplying by this matrix where you've removed the P row of the identity removes the P row out of the original matrix, out of the matrix A via matrix multiplication. And then, like I said, the exact same proof for the columns. It's basically exactly the same. And note that these proofs really aren't too shocking or interesting. They're very just unraveling definitions and again, a lot of the proofs that we end up doing are just like, hardcore index management. All right, and speaking of that, typo right there, typo here. Was the previous slide of all those errors? Yeah, no, the previous slide's all right. We'll clean up here, right? This should be a CP. Sorry, that should be a CQ. I might just use P and Q to be different. Nothing particularly special. But, in the sake of... Alright. So let's keep moving. So something that we're going to use, which is pretty easy to verify, and this proof will give us a real flavor for what it's like to actually work with these matrices. So we verified that multiplying by RP or CP will delete a row or delete a column. And it turns out that if you were to multiply in our P and a CP, where the P row and P column are the same, if this is, we're talking n by n plus 1, then this thing will be the n by n identity matrix. So, for example, take the 3 by 3 identity matrix. If you delete the second row and the second column, you'll just get the 2 by 2 identity. Likewise, if you take the 3 by 3 identity, delete the first row and the first column, you'll get the 2 by 2 identity. So we're going to use this fact. So we need to prove this because we're going to use it. But this is a good proof to look at because it's going to give us a pretty good flavor for how working with these matrices R and C is going to go. All right, so pick indices between 1 and n. Our goal is to show that the jkth entry of this is indeed the Kronecker delta. All right, but we got a few cases we got to handle. So let's say we haven't passed the pth column yet. All right, well, as we just proved then, this matrix multiplication will delete the kth column of this, but the pth column of this, but since we haven't gotten the p yet, nothing has changed. So now, if I look at the jth entry, where j has not reached p yet, then the jth entry will just give me the Kronecker delta, and that's what the identity matrix equals at jk. Now, let's say p has exceeded the row. So we took care of the case where p did not exceed the distinguished row that we're deleting. Let's say it does exceed or equal the row we're deleting. Well, that means since k is strictly less than p, and j here then is strictly less than j plus 1, then j and k here must be different numbers, and so must be j and k, j plus 1 and k. So if we were now going to look at the jth entry of this, well, as we noted, k here didn't exceed p, so we haven't shifted anything yet. But now the j has exceeded p, so this will shift by j plus 1, but j plus 1 and k must be different, so that has to equal 0. J and k must be different, so that has to equal 0, which lines up with the identity. So again, to follow along with that, we first are looking at the case where the column hasn't exceeded the one we're deleting, and then we look at where j could be. So j is either before the row we're deleting or after. If it's before, then, yep, still lines up with the identity because this will just be the Kronecker delta. And if we're exceeding the row that we deleted, then the j gets shifted by 1. But given the setup we're in, j, k, and j plus 1 are all different numbers. So these will always spit out 0. And there we go, that equals the identity matrix. And now, all right, let's say we're past the column we're deleting. So note what we're doing. We're working from right to left. So you got to deal with the fact that you're multiplying by the column deletion first before you can get to this matrix. That's going to be the trick we're going to basically pull. Okay. So since we have passed the column we delete, then the column gets shifted by 1. So then we do the same breakdown. Let's say the row we're in hasn't exceeded the row we're deleting. Well, then if we look at jk, well, the k gets shifted by 1, as we noted, and then that will give me j and k plus 1. But by the construction here, k plus 1 and j are not equal, so is j and k. Note that j would be strictly less than k in this case, so they all delete out. So there we go. That will still line up with the jkth entry of the identity. And then finally, if j has exceeded the row we delete, well, since we exceeded the column that it was deleted, we shifted the k by 1. And that means we then shift the j by 1, since we exceeded the j there. And note that the Kronecker delta spits out 0 or 1. If it spits out 0, these numbers are different. If these numbers are different, then j and k have to be different. Because if j and k were equal, then these numbers were equal. And likewise, if j and k are equal, then these numbers are equal. So this is actually a fact of the Chronocle Delta that gets used. If you shift the inputs by the same number, then the value doesn't change. Right, and there we go, we get the identity matrix there. So that completes the proof. So we've gotten our first flavor of working with deleting rows and columns, and here we see it basically grabbing us the identity matrix. So this is a fact that we will use. We'll see in a little bit. And that is time for today. So I haven't quite got there yet to stating the recursive formula, but we're getting there. So we'll probably state it on Thursday. And then we'll probably on Friday prove that it is indeed what we claim it to be, and then we'll finally get to the magic matrix so that A times B is the determinant times the identity, and then that will wrap up the story. We'll move over to eigenvalues at this rate. So, yeah, that is it for today. All right, so we're getting there. We're slowly working there. All right, stop the recording.